Okay, just had to announce. Just had to announce on a couple of groups. So we're online now. Amazing. It's been a weird morning. The farm, the farm's internet connection sort of got messed up, and so we didn't have internet today. So basically had to start streaming quite late, which is what 2 hours later than normal. But just going through the motions. That's what I'm doing. Going through the motions. Yeah. Because but right now we also have this particularly notorious issue that we're facing, which is trying trying to get this thing to work. And the way I'm doing this now is I'm attempting to, yeah, that's better. I'm attempting to run, let's run a couple of other examples and see how they work. I have a feeling this one won't run because this run has been shown to be broken before. But I do have another development board over here, which is STM32F4 Discovery. And this board has has onboard digital mic, and plus the digital mic, it also has an I2S I2S peripheral that is connected to the mic that we want to use. Okay, cool. So what I want to do is basically, I don't think it will work before because this application usually crashes because it doesn't have enough RAM. I don't think it'll work, but what I'm going to do is I want to run it, and if it does run, we can use that sample to fix our application. Yeah. So it's feel free to ask any questions if you have them at any point. But right now, what I'm going to do is I'm going to start trying to run this. I mean, I'm just going to attempt on the ST once. And if it doesn't run on the ST, we're back to an NRF application. I do have some notes that we can follow through and stuff. So let's basically west flash dash r open OCD. Okay, let's see if that flashes. That is flashing, and yep. And then I probably need to run this guy over here to see if we get anything. And I probably can't do a reset code example. Yeah. We get a hard fault. We get a hard crash. That's a problem. I don't want to fix that right now because that's going the opposite direction. But this is actually a good thing. This is a good, yeah, you can see the program counter is 0. So there's a problem. There's probably like some sort of memory error. But we'll do another stream on hard faults later, or rather on faults later. Today, let's focus on debugging the thing that we are going through. So I'm gonna disconnect this, and you're gonna see things like go off and stuff. I was hoping just by bumping down the memory, I could have gotten that work quickly, and we could have used that as a sample, but I can't. So what I'm gonna do is, I thought the ST had more memory than my NRF STM32F4 Discovery. I for sure thought it had more memory than my NRF, but it might not. So, like, how much RAM does this thing have? More than 256K? It's funny because we have like people in the group, in some groups, talking about like insane amounts of data, and here I am running on, oh yeah, 192 KB RAM. Cool. So it is less than the NRF. Okay, cool. So let's go back to our original problem. Remember this board? It's a BLE board with a microphone with it. And what we're trying to do is get it to periodically record audio. So every 2 seconds or something of the sort. We're trying to get it to periodically record audio. And I think we're doing a couple of mistakes that I have been looking. I've sort of been going through. When you have a few minutes, I sort of been going through some notes and stuff and trying to see, and this is basically the notes I have. We need to check the microphone data format, and then we also check the alignment of bits so that we don't collect garbage, because if you do a left aligned, you could, and you're collecting the right bits, you're basically getting just garbage. And if you do a right aligned and then you're collecting the left bits, you're in garbage. And then the other thing I think we need to check is how to use mem slabs, and then how much time do the mem slabs we are going to use allow for recording, because I also have a feeling we could be starting and stopping the thing so fast that it's just not getting anything. And then I did find some older links, like the second one, which is a link to older Zephyr documentation. But let's quickly run this code and see what happens. So this is not where we want to be. This is definitely not where we want to be. We want to be back up into applications, ls cd Zephyr custom ls. I think ls. Do I have a compile commands? Yes, I do have a compile commands here, so we should be okay. And then this we can also see applications. No. Now we're in Zephyr applications. Zephyr custom. Okay, so let's be here so that we can do some stuff here, and then once we're in here we can do so first of all, git status. Where are we? Git status, git diff. This is just this was more debugging by me. Okay. Git checkout. Just check this out. No, check out where we are now, so that we are on this path. And then what I want to do is just build that up and run it, and then we can see. So west control R nrf 5 to, yeah, let's do that. Let's build that for nrf. And I've discovered the nrf has more memory than the ST. That's quite cool. Anyways, as I start, any questions so far? Does anything not make sense? Does anything make sense? If you have any questions, please feel free to drop them, man. Drop in the chat. You can even ask, what the heck am I doing? And then I'll answer what I'm doing. Okay, cool. While this builds. But basically we have an audio application that's not that is not recording audio as reliably as we want it to, and we're trying to fix it. So that's what we're trying to do. We're trying to fix that. We're collecting the packets periodically the way we should, because once we have the packets, we want to do some classification or deep learning on the packets, and then we'll see from there on. I should try and make my builds go faster, but that's also another problem. That's a problem for another platform for another day. But so once we have this here, we can just do clear. We've built the app, so we can just now go to Control R. I think it's Control R -- hardware. Yeah, this one. Let's pack it. Let us pack that into a pack.zip. Package generate. Yeah, pack it into a pack.zip. Cool. So that's fine. Let's pack it. It's packed into a pack.zip, and then Control R. I think we need something like BFU. Yeah. And then I'll always do this once a stream. I'm gonna put it in bootloader mode. You should see a red light. There's a red light over there. So the app is in the board is in bootloader mode. I keep calling it an app. So now I can push in some code into it. Yeah. And then as I'm pushing that code into it, this is the command I'll run once the thing is installed. I can actually tell from the LED, I don't need to be looking at that, it's on. Let's run that. Yeah. So yeah, you see it records the first sample, records another sample, and then eventually what happens is, as you can see, we start running out of data. We start running out of space. And it fails to allocate next buffer. We can actually go find that issue. We should go find that line. We should go find where that line is failing. Yeah, and then let's go back. We're in Zephyr now. No, we're not in Zephyr. So let's get into Zephyr, and let's get into drivers, and then let's get into, is it audio? I2S? No, I have a feeling it's gonna be in I2S itself. So I2S is gonna be itself. I2S. Yeah, I2S, and then there's gonna be I2S NRX and FRX. Cool, NFRX. And then in here with what is the thing that we are failing? Failed to allocate next RX buffer. So let's look at that. Failed. So here, get next RX buffer. So it gets, oh yeah, this is so cool. We can see now what is happening. So look, our thing does the allocation. Do you see? It does the allocation. So I was thinking I would have to do something about the allocation and deallocation. So now we're learning. So it tries to allocate, and then it doesn't. It actually doesn't. It doesn't work out. So the other thing, so that's cool. So this is good. It tries to allocate, and then it doesn't. It's not able to allocate the. It's not able to allocate the memory block on the memory slab. And the reason that would fail. Memslab alloc. Memslab alloc fails. Let's go into the browser, and then let's go look at memslab alloc. Memslab alloc. So let's look at this function from Zephyr. Memslab alloc. Memslab alloc. So we're looking for memory slab APIs. We want to memslab alloc, and I want to know what it might reduce. Mem, E again is 11, E in val is, so 12. 12 is what? Zephyr mem. So why is that failing? Zephyr API error numbers mem. If this is if mem is 12, then we found it. Mem. Why am I doing this? Mem. Not enough memory. Okay, cool. So that's fine. That is exactly okay. So that is mem. That fixed that does. Okay, cool. So that means it can't get memory. So what is happening is basically, as you saw, if we can do this. So I'm gonna turn this off. And I'll put that up. And I'll turn it on again so that we can go through it again. 1, 2, 3. So what happens here is it manages to do that is one sample, two samples, three samples, four samples, five samples, and then it starts failing. Cool. So five samples, five blocks, and then it starts failing. So let's see if the problem is how we're doing. Let's see read. What does read do? Let's see what does read do. So this is an I2S driver. So yeah, let's see G. Okay, cool. It just makes a driver like normal. Does it have a device API somewhere? Pin control defined, that's fine. Pin control defined. I want to see if it has a device API. Device API, cool. So there's a read. That's fine. So I want to go to this. I want to go to this guy. So, G. Okay, cool. NRFX underscore read that. So yeah, it is. Here it is. This is the function we want. So I want, what I'm basically trying to discover is whether read actually deallocates. Okay, because we've discovered that read allocates. So let's see. Read allocates. So because it goes get next buffer. Okay, message get driver state. Yeah, I also want to go through I2S states. That was also the other thing. So if not data rx configured, log error, device is not configured. Okay, cool. If log released, okay, cool. Log ddb released rx. Okay, cool. If no message, return error, IO error. Yeah, cool. So no. So where did we get that failed before? Failed. No. Fail to allocate next buffer. Get next buffer rx. Get next buffer rx. So who is calling get next buffer rx? Get next rx buffer. So who calls you? Start transfer, supply next buffer, get next rx buffer. Start transfer. No. This is a TX one. Feels like. Get next rx buffer, get next rx buffer, next rx buffer. So what I'm trying to find out is, because I know this is what is failing, and it's failing as a part of read, but I don't know. I'm trying to follow this through to see where I'm trying to see where this actually read next. If device.rx configured, if the device does not have, so message get. Okay, message queue get. There's a queue item. And then once we get it, message queue get. What does message queue get do? Message queue get. What do you do? It gets a timeout, it gets some data. what does it return? What do you return? What do you give back? Returns message received, no message, waiting period run out. So cool. So k message queue get driver data rx queue. Yeah, that's a queue. That's a queue. Wait. That k message queue get takes what? Takes a message queue and some data items. Okay, cool. So takes a message queue, data, address of area to hold the received message. Okay, address of area and buffer and that. So, but where is that? So this is the third thing, which is driver state. Is the driver state an error? No. Okay, no, wait. Is the driver state not in error? Wait this long, and then do that. If ret is equals to do that. Else return ret. Wait. This is just read. This is just read. This is if we were using a sensor, this would not be fetched. It would be get. So this assumes sorry. So this is I think it's start transfer or something. No, this is configure patch queue. Let's look at start transfer, trigger start or something. Read is fine. I think what it's telling us is that there's no deallocation, because if there was deallocation, it would be in here. It just returns the mem block here. Which also promotes what I was seeing here. Zephyr. I want to go to samples. I bet you I based mine on either echo or something. Samples driver I2S. Do we have any questions? No questions so far. Samples driver, and I think I either use echo or codec as my base, whichever one is the NRF 52840 DK. Cool. So this was my base source. Let's look at main. I'm not going to be using the codec, obviously. What I want to see is how they're handling. So the thing I'm going to look at mostly is the process data function, process block function. So you pass in a block, and there's this mem set. You see here, mem set echo block, 0 size of echo block. We can try that. In our app very quickly. Mem set echo block. Mem set the block 0 size of block. Yeah. Cool. We can do that. PF Zephyr custom. So this is CD and then so here. That's fine. I should just main here. Not in main. I think we want to go to audio service, and then in audio service somewhere in here, see here, and this shouldn't be drop. We shouldn't use drop. Let's use stop here, and here's the reason we want to use stop and not drop. Zephyr API documentation. Let's look at that. Let's look at I2S. 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 I2S interface. So let's look at this. The reason I don't want to use stop and I'd rather use I don't want to use drop and I want to use stop is because I found this out in my readings over the weekend. I2S trigger. What is it? I2S trigger stop. Yeah, I2S trigger. I2S trigger. Yeah, I2S trigger takes. Yeah. Where is the I2S trigger stop? I2S. It was so much easier because look, Zephyr I2S. Yeah, the one that we were using before. Remember just now it was I2S drop here. Okay, I can excuse. It was I2S drop. That's what we're doing. So the thing drop does stop the transmission or reception immediately and discard contents of the respective queue. Okay, so that's not actually what we want. We would rather it stop. Look, so when we say stop, it stops it, and then it stops it, and then it stops it at the end of the current recording block. So it records the current block that is broken. It's recording and then it stops. Let's actually in here rather than stop capture, then drop any packets. So let's do two triggers. I2S trigger, I2S dev. This is I2S dir rx. Let's do I2S trigger stop. Okay, so what does that do? It does the normal stop that we want, the actual functionality that we're aiming for. It does the stop, and then we call a drop after, and the drop we're calling after is just for sanity. We're just calling that so that in case there's any residual packets in our buffers, they should be discarded. Okay, so this is just a cleanup of anything that happens after stop. Okay, what I want to do in here is I want to try that trick that I'm seeing in this code repo here. This memset echo that block to 0, and what we're doing here is just setting it to 0. We're cleaning it. Okay, memset c. Okay. Can I get something a bit less? Okay, cool. So memset here. What does it do? Oh, come on. The C library memset function of type void accepts 3 variables as parameters that copies the character C, an unsigned character, to the first n characters of the string pointed to. So this just basically sets some memory to a certain value, and it's using kind of a string here to make it they're using strings, but you can put in any sort of buffer that you want. Okay, cool. So here let's do a memset. I would much rather use memblock. I would much rather use the size of memblock. I would much rather use the case memslab API, which we'll try just now. But if you recall correctly, we have tried it before, and it was a bit of a bother. It didn't really work out. Okay, So let's look at this code here. So it's memset eco block, size of eco block, mem block. So cool. And the eco block here is just a passed in eco block. This is so odd. They're not doing anything to the mem block. They're just copying samples over from the mem block into here, and then they never do anything with the mem block itself. Control F mem block. Let's walk through this code and see where it's used. So they just copy from the mem block into there. That's fine. And then anywhere else they allocate a mem block. This is kind of odd. You see? Block size. Perfect. They do memset mem block there. So memset mem block, and I can use a primitive that we have before and say block size. Yeah. So they do that before. They do that after. When is that happen? So memset mem block here. No, this is before using it. Do you see? They allocate it, they set it to 0, and then they use it. They don't use it at all. This is before using it. So let's go next again. Next again. No, I don't want you. I just want here. Yeah. Process block data. And then that, and then that, and then that, and then we're back again. Let's try and reset it here and see what happens. Let us try and reset it here. So block. Oh. Don't we have a block size in here? We do have a block size. So block size. Okay, cool. So let's run this again, just the normal way, and see if it works. Okay, so let's build it. All we've done is we've just added some clearing of the. We read it and then we clear it, and then I can probably do something like here just to make it more. Just to make it int samples. Okay. Let's do a little for int n equals 0, n is equals less than 10, n plus plus, and then in there let's do that. Let's do like this. Actually, let's put this logger in the for. And then in here, we can go here and do this. And then we just want to see if we're getting distinct stuff, okay? So n, and then that's fine for now. Okay, that's fine. And then it's also some time operation. It just allows the driver to do other stuff in the background so that we can do that. Okay, cool. Let's build that. Let's build that and see. What we're trying to do is clear the memory. I will, as it's building now, we can go back and look at the APIs so that I'm not doing stuff just in my head and you guys are watching. You people are watching. Might not all the guys. Okay, cool. So that's building. So let's look at Zephyr K memslab. K memslab Zephyr K memslab. The way works, memory slabs. Memory slabs dynamically it's dynamically allocated memory that you pre-allocate in compile time so that you can use it in runtime. A memory slab is a kernel object that allows memory blocks to be dynamically allocated from a designated memory region, or memory blocks in a memory slab have a single fixed size, allowing them to be allocated and released efficiently and avoiding memory fragmentation. So memory fragmentation is when you use a lot of holes in your memory, and then you have memory, but you can't use it because there's no block size the way you want to use. Blocks are allocated at compile time. Yeah, at compile time, because you say the size of the blocks you want, and then you can use them. You can use dynamic memory, but not allocate it later, so it will always be there. A memory slab must be initialized. I'm sure I am doing something like kmem slab init. Is it because yeah, I understand. So because we are using kmem slab the macro, we are using the macro. So kmem slab init, and there's going to be a macro, I think kmem slab define, statically define and initialize a memory slab. So in our code we just finished building, let's packet. Cool, perfect, we packed it. Now let us push it onto the board. I'll put the board on bootloader mode, and then we push it onto the board. You should see once it starts, this will die. That has died, so it started. So cool. That's running. Let's run it here, and then let's see what happens. Okay, cool. Yeah, you see what's happening? So we've started running into the memory errors again. Fail to read, fail to allocate next buffer. Because we're running out of memory. I don't understand. We have so much memory. Like we're building. If you look at our building, we're using 66% of the RAM. So we have, that's some big blocks. And also the other thing I notice is we get. So let me just remove it. Let's do it. Let's run it again and observe. So the other thing I've noticed is we get, oh yeah, we're getting good samples, and then we get zeros after that. You get zeros after that. What happens if we don't zero it out like this? Because after we do that for the first one, we kind of lose everything. So let's see. Let's build it. So what was I walking through before? The macro kmem slab define, which we are using in our code, which is what we're using in our code, is kmem slab define static, actually. Define static. So okay, statically define and initialize. Yeah, so that's what we do. It basically it defines it in sector static, in sector static. Let's look at that. Well, that statically define and initialize a memory slab in user provided memory section with public non-static scope. The memory slab's buffer contains slab num blocks, memory blocks that are slab block sized bytes long, and the buffer is aligned to a slab align byte boundary to ensure that each memory block is similarly aligned to this boundary. Yeah, sorry. That's the thing that prevents the allocation stuff, the fragmentation stuff. So we just remove that. Let's see what happens now once we remove that, okay? And I don't like that my samples are so cool. Let's pack it, I think. Perfect. And then I'll put my app in bootloader, my board in bootloader mode. And then let's do a push. Let's just push it in. And that should kill this. That's what we want. And once that's killed, let's let it put it ready to run it. And I can see it's still flashing. Cool. Let's start it here. Let's see. I wish to see different kinds of data. Yes, this is good. This is good. So it goes up a few rounds and then it starts just going to zeros. Yeah, that's fine. And then it went to a zero and then that's okay. So that's cool. That's entirely cool. We are getting data. We are getting actual data, but we keep running into... I'm very confused. I'm very confused. Yeah, and that thread is sleeping so short. It's not even sleeping that long. It should sleep 2 seconds. So that should be like 2 seconds in between. 1, 2, 3, 4, 1, 1,000, 2, 2,000, boom. 1, 1,000, 2, 2,000, boom. Yeah, it's sleeping 2 seconds. I wish I should have like a clock I can pull on the screen and then I can go for it. So, how come our buffers? So let's look at kmemslab free. Kmemslab free. Free memory allocated from a memory slab. This routine releases previously allocated memory back to its associated memory slab. So it takes a block, it takes a slab and a block. So let's try that. Let's try kmemslab freeing it rather than setting it to zeros and see what that does. The other thing I saw is that they set it to 0 before they use it. So basically before read. Let's try set it to 0 before reading, because then that sort of follows the logic here, which is, you see, they are located, which I expect happens in the... So they, if, so they allocate the mem slab. Okay, no, wait. But I don't want to do this. I don't want to allocate because I've just discovered that inside the NRF I2S, so Zephyr project Zephyr, I do not want to allocate it again because I have discovered that read actually allocates. Read does allocate. What do you hand into read? What do we hand into read? I2S read memblock size. Cool. I2S read memblock size. And we do already give the I2S driver our memslab here. So it knows our memslab, and if it knows our memslab, then read can allocate. Let's walk through this code slowly, bit by bit, and find out how it's gonna. This is such a cool guy, Jamoni. I don't know. It could be a gal as well. I don't know them, but they're very cool. They do very cool stuff. I2S, and then I want to look at I2S NRFX here, and then I know read. We discovered read. How long is this line? How many lines of code? 870. Yeah, that's fine. That's mostly error checking. I promise you. Something like here, and then I should be able to find I2S read. Yeah, you. And what I'm basically showing here is that read just gets start. We basically want to see it start. start transfer. Okay, cool. So if if it's both, no, it's not. If active if driver dot active direction is not equals to rx, tx to be started. If it's not equals to tx, rx to be started. Get next rx buffer. So there's this guy. Get next rx buffer. There's this guy, and that does a memory slab allocate. So maybe we just do a mem set on that mem block, and then we see if that changes anything. Let's just do a mem set. So I mean, now we're just basically walking through everything, because they do a mem set here. See, they do an alloc before that. See that's before in here. That's before in here. This mem set is before in here. So let's just try it. Mem set, but that is before trigger. I know they do prepare transfer. Let's go into main. So they do devices ready, blah blah blah, trigger, prepare transfer, case take, Where's your trigger? Where's your trigger? You never you triggered it way before. Where did you do your trigger? If trigger command is not start, then after they've started it, then they would do this stuff. So it's after trigger, after start, cool, after start, but that mem set is done after start. Where's the mem set being done now? So they do prepare transfer, and then they do a trigger. Prepare transfer. So you see prepare transfer is over here. Then they do a trigger. So let's do a mem set. This is mem set. Mem set, mem block 0 block size. Can't even check on the result of this because sure, just do that. It's not allocated. Why do I want to do an allocate there? Do I really want to do an allocate? I don't want to do an allocate because it's gonna be, you're gonna call allocate on something allocated already. Yeah, let's do this just after we trigger, before we read. Yeah, let's see. Before we read, let's see. Mem set, mem set, mem set, mem block 0. I feel like this is just, I'm messing with memory that is being used by the, driver here. Block size. Someone's gonna say this is why you use Rust. Okay, cool. So yeah, that doesn't like it there. either, so that's fine, that's okay. And if I go in here, yeah, no, this one, can I find k mem slab free tx buffer? I see a free. I see two frees. Free rx buffer, free tx buffer. I don't know where they're called. If status that and stopped or stopping that, we're gonna free. So we don't even need to free the data. Log 1 10 block samples. So I want it to be less lines. And then there's that, and then in here I just want to sample, log the sample itself, log 1, the sample itself, and I don't want to do an n. And then in here I want to do log 1. I just want to do an n. I know. Let's build that again. I wonder if we have KMemSlab APIs that tells us. I wonder if we have KMemSlab APIs that tell us. Let's use this. Yeah. I'll do that. I wanna use KMemSlab num free get. It takes a memslab. And then just run it before after. Let's run this guy first. Let's pack. And then let's do TTY-SEM0. These are like really nice. This is really nice data, but now it's just not working, man. Okay, cool. So I'm removing that. I'm gonna remove the 10, the 410 here, and we can just do fast sample, and it's like, or like sample number 5 or something like that. Sample number 5 in block. Yeah. samples 5. That's fine. That's okay. That's fine for that. And I know it frees itself, so that's as well okay. So what I want to do is, before I trigger, let's do here. Before I trigger, I want to kmem slab num free get. How many free blocks do we have? Kmem slab num free get. Is that the, yeah? And then I'll take a mem slab, and then I can actually just go log int free blocks. Okay, and then in here we'll go like free blocks is this, free blocks is this, is equals to that, and then let's log one this guy, log one free blocks in the slab, and then let's do that, and then that, and then that, and then free blocks, and then let's do that. And then what I want to do is free blocks in the slab. This is before start. And then let's copy that Y, and then this J, let's do after start. Let's do after read, okay, and then let's do after stop, after stop, and then here let's do after drop. Let's run that. Let's run this code and see what happens. I mean, it's been an hour of streaming, so I'm probably going to stop soon. But what we're basically doing is we're discovering this thing is sticky. So there's some surface area of this code that we don't know about. That's what's happening. There's some surface area of this I2S code that we don't know about. Or something is wrong in the driver and we have to go and fix it. Because I do call stop in between my recordings. And because I'm calling stop in between my recordings, as we've seen the code here, as we've seen this NFRX code, it should free it. There's free here if it stopped. So when getting it stop, it will free it. It will free the RX buffer. I mean, last TX buffer. Anyway, basically, yeah, free RX buffer. The RX buffer is freed when I stop. So there's some area of this code that I don't know about. There's something I don't know about, or the driver itself is doing something that I'm not expecting, and then this is causing a break. So we've built that. Let's pack it. And then after we pack it, let us push it out to the thing itself. Let's put it on the hardware. I can probably tell on this side when it's done because I'll see the blinker stop, 50%, It's done now. Let's start that logger. Let's see. So free blocks 6, 5, 4. Do you see? Do you see what happens? Yes, 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 we found it. We found it. So our blocks are never freed. Let's see. Is this mem slab, this free tx buffer here, free rx buffer, free rx buffer, this one, okay, mem slab free. This is actually the mem slab we pass in, but it's never freed. It's never freed. Okay, cool. This is amazing. This is amazing. This is cool. So let's try and actually call kmemslab free at a certain, let's call it at a same point and see what happens. Let's call it at the same point and see what happens, because it's quite cool. You can actually see our errors happening. You can see our errors happening, and this is exactly why we needed to do this. So we can actually see our errors happening. So this is fine. So let's do that. Let's start that. And what you'll notice is, look, I have eight free blocks, 6 free blocks, 4 free blocks, 3 free blocks, 2 free blocks, 1 free block, 0 free blocks, and now we cannot allocate. So, I don't know if you guys can hear roaring in the background. My kitten just got a lizard, and she's going crazy. So, I promise you, she's completely fine. There's no one's bugging out, nothing. There's just a kitten in the background hunting. Okay, cool. So we actually have a root cause for our error. We can see that our memory slabs are not being freed. Let's try let's try and free a couple and see. Okay, memslab free. Okay, memslab free. This routine releases a previously allocated memory block back to its associated memslab. So it passes it pointer to the memory block. So let's, oh my word, Yin, can you not do that? Anyways. This is insane. So okay, cool. So let's go after stop, and I think we still have the mem block here. Yeah, let's go after stop, and then let's call k mem slab free, and I think that's k mem slab free, and then we can pass in our mem block. Seriously? And then we can pass in our mem slab and our mem block. Mem slab and our mem block. It could also be the way I'm utilizing the blocks, but we'll see. It could also be the way. Does this return a void? I cannot check. It's a void. Okay, cool. So let's do that. Let's build, and then we'll finish at that. That's actually already good. So we already know what the problem is. Our mem slabs are never free. Let's see if freeing them does fix the issue. I'm sorry about the roaring kitten in the background, the hunting kitten in the background. So this is going to be the final run, and then basically we've discovered the problem. our mem slabs blocks are never freed. So basically, we end up running out of space to we allocate any more memory that we need to use. So let's see what happens. The expectation is that the driver frees this stuff, and the other thing that I might not be doing is I might not be waiting for the states good enough. I might be transitioning between states so quickly that I'm not letting it take effect. So let's see. Yeah, don't get kittens. The kitten is this size, I promise you. It's so small. And then let's go into that. Go into bootloader mode. Pack up or up. Let's get it up there. So this is going to be our actual thing. And let's see. Okay, let's start the logger. Let's see. 8. Now it just crashes. It doesn't keep going. The moment I free a block, it just crashes. Okay. One more try. Let's free a block at the same spot after we've actually used it. Because after stopping, we might be running into some stuff. And then here, I want to just add a sleep sec 1, just a little sleep to make sure all the jingles are jingling okay. Okay, this is just start trying to release it at the same spot, and then we see what happens. I have a feeling I'm not waiting for the transitions of the states. Nice. And if I'm not waiting for the transitions of the states, nice, I'm skipping from state to state without... You see these states? There's this I2S states. There's this I2S states. This one's here. I have a feeling I'm skipping from these states quite quickly. And I should wait until the state has changed before doing the next thing. Although this is a problem because in I2S is a continuous thing, so it just goes on while I'm waiting, so, and that's a problem. But let's pack it. Okay, cool. And then we would like to push it onto our board. This is the final run for today. It's pushing onto the board. My kitten's going nuts in the back. Let's see what happens now. Releasing at the same spot. Okay. 8. It just it stops. So I want to catch them from the beginning. One, two, let's. Yeah, I see. So it just goes twice and then it stops now. It just stops. But that's because I keep But now, here's the thing. I've used that block, I freed it, it stays at 8. Okay, cool. So we've established the actual issue. Our memory slab blocks are not getting released, and that's why we're running out of memory. So there's some intuition I'm missing on how to use this API, which I'm going to go and research, and then we'll see if we can keep on with it tomorrow. But this is cool. We discovered our root cause of the error. This is essentially what we needed to do. Now we can start trying to see how it can be fixed. Anyways, thank you so much for coming. That has been an awesome session today. That was pretty amazing. I'm pretty chuffed that I actually ended up stumbling onto that. And I think we can actually start making progress towards the solution of this, because now we know what is actually the problem. Thank you so much for hanging out with me. Sorry the stream was 2 hours late today, but still got to it, and I'm really glad for that. Thank you. Cheers. See you.